cosm. Whoosh.
There's a moment in every scientist's career when you realize that what you thought was a simple question has layers you never imagined. For everyone studying JWST-7329, that moment came early and it hasn't stopped coming. Every answer spawns 3 new questions. Every measurement reveals another mystery. It's like peeling an onion. Except this onion is 13 billion light-years away and made of stars. Let me tell you about the gas. Because when we talk about star formation, we're really talking about gas. Stars are born from clouds of molecular hydrogen, dense and cold, collapsing under their own gravity. No gas, no stars. It's that simple. But getting gas into the right condition to form stars, that's the complicated part. In JWST-7329, something remarkable is happening with the gas. The spectroscopic observations show strong emission from ionized hydrogen, the classic signature of star formation. But there are also fainter lines from molecular tracers, hints of the cold gas reservoirs that fuel the star-forming regions. These lines are challenging to detect, requiring careful analysis to extract them from the noise. But they're there, and they tell a story. The molecular gas in JWST-7329 appears to be concentrated, not spread throughout the galaxy, but clumped in specific regions. This is unexpected because in such a small system, turbulence and feedback should mix the gas, creating a more uniform distribution. But the observations suggest otherwise. There are cold, dense pockets where stars are actively forming, separated by regions with less gas. This clumpy structure might be key to understanding how the galaxy survives. If star formation is localized, if it happens in discrete bursts rather than continuously throughout the galaxy, then feedback is also localized. Supernovae explode in specific regions, heating and dispersing the local gas, but not necessarily affecting the entire galaxy. Other star-forming regions can continue undisturbed, maintaining the overall star formation rate even as individual clumps are disrupted. This is called stochastic star formation, and it's particularly important in small galaxies where the number of massive stars is limited. Instead of steady, continuous star formation, you get bursts, periods of intense activity followed by quieter periods. The galaxy breathes, inhaling gas and exhaling stars and stellar winds in an irregular rhythm. But how do we know this is happening in JWST-7329? The spectroscopic observations provide time-averaged information. We're seeing the galaxy as it was at one moment in cosmic history, but that moment lasted thousands of years from the galaxy's perspective due to light travel time across its extent. We can't directly observe the bursts unless we're lucky enough to catch the galaxy during an active phase. What we can do is look at the stellar population. By analyzing the spectrum, we can estimate the ages of the stars. If star formation were continuous, we'd see a smooth distribution of stellar ages. But if it's bursty, we'd expect to see age gaps, periods where few stars formed, separated by periods of intense formation. The preliminary analysis suggests the latter. There are hints of multiple stellar populations with different ages, suggesting episodic star formation. But the uncertainties are large. Stellar population modeling is complicated, especially at high redshift where we're dealing with unusual chemical compositions and potentially different stellar evolution pathways. More detailed observations are needed to confirm this picture. One way to test the bursty star formation hypothesis is to observe JWST-7329 in the far infrared. When massive stars form, they heat surrounding dust, causing it to radiate in the infrared. The intensity and spectrum of this dust emission tells us about the current star formation rate and the dust properties. If star formation is bursty, the infrared luminosity might be unusually high or low compared to the average implied by the UV and optical emission. Unfortunately, far infrared observations of such a distant, faint object are extremely challenging. Webb can reach into the near and mid-infrared, but not the far infrared wavelengths where dust emission peaks. For that, we need different telescopes. ALMA, the Atacama Large Millimeter Array, can observe at long wavelengths where dust emission is still detectable, but even ALMA struggles with objects this faint and distant. Proposals have been submitted to observe JWST-7329 with ALMA, but telescope time is competitive. Every astronomer wants to use these facilities, and there aren't enough hours in the year to accommodate everyone. Committees review proposals, ranking them by scientific merit and feasibility. Only the top-ranked proposals get scheduled. It's a Darwinian process, survival of the most compelling science case. This competitive system has advantages and disadvantages. It ensures that telescope time goes to the most important science, as judged by expert reviewers. But it also favors conservative proposals, projects likely to succeed over risky ventures. Truly innovative ideas, which might fail but could revolutionize the field if they succeed, often struggle to get approved. There's a tension inherent in how we allocate scarce resources. For JWST-7329, the science case is compelling but not guaranteed. Detecting molecular gas and dust at this distance is difficult. The observations might fail, wasting telescope time. But if they succeed, they could transform our understanding of this enigmatic galaxy. The proposals are pending, and we'll see whether reviewers judge the risk worth taking. Meanwhile, other lines of investigation are proceeding. One particularly interesting avenue involves looking for chemical signatures of specific stellar populations. Different types of stars produce different elements. Massive stars produce lots of oxygen and neon through core-collapse supernovae. Intermediate mass stars, in their asymptotic giant branch phase, produce carbon and nitrogen. Lower mass stars in binary systems can lead to type Ia supernovae, producing iron. By measuring the relative abundances of these elements, we can infer the stellar population that enriched the gas. If JWST-7329 shows enhanced oxygen relative to iron, it suggests rapid enrichment from massive stars without much contribution from type Ia supernovae, which take longer to explode. If carbon is enhanced, it suggests a significant population of intermediate mass stars reached their late evolutionary phases. The current data shows oxygen enhancement, consistent with young, massive stars dominating the enrichment. But the iron measurements are uncertain, plagued by weak spectral lines and contamination from nearby emission features. Better observations with longer integration times could clarify the situation, providing tighter constraints on the chemical evolution history. There's also the question of primordial gas. The very first stars formed from gas with no heavy elements, pristine hydrogen and helium from the Big Bang. These population 3 stars were likely very massive and short-lived. Their deaths would have enriched their surroundings with the first heavy elements, enabling the formation of population 2 stars with small but non-zero metallicity. Could JWST-7329 contain remnants of this primordial enrichment? Could we detect gas that still bears the chemical signature of population 3 stars? It's a tantalizing possibility. The galaxy is so early, so close to the cosmic dawn, that it might have formed from gas enriched by the first stellar generation. The spectroscopic data doesn't show direct evidence of population 3 signatures, but absence of evidence isn't evidence of absence. The signals might be too weak to detect, hidden below the noise, or they might have been diluted by subsequent enrichment from population 2 stars. Detecting population 3 chemical signatures is one of the holy grails of high-redshift astronomy, and every galaxy from this epoch is a potential candidate. Let's shift gears and talk about magnetic fields. You don't often hear about magnetism in discussions of galaxy formation, but magnetic fields play a crucial role in regulating star formation. They provide support against gravitational collapse, slowing the rate at which gas can collapse into stars. They channel gas flows along field lines, affecting how galaxies accrete matter. They're an essential but often neglected component of the story. Do we know anything about magnetic fields in JWST-7329? Not directly. Measuring magnetic fields at such distances is extraordinarily difficult. The main technique involves observing polarized emission from dust grains aligned by the magnetic field, but this requires exquisite sensitivity and angular resolution beyond current capabilities for such a distant object. However, we can make educated guesses based on theory and simulations. Magnetic fields should be present, generated through dynamo processes as the galaxy rotates and differentially shears. The strength of these fields depends on the rotation rate, the gas density, and the turbulence level. For a small, rapidly star-forming galaxy like JWST-7329, we might expect relatively strong fields compared to its mass. These fields could help explain some of the galaxy's properties. Strong magnetic fields could provide additional support for the gas, reducing the star formation efficiency and allowing the galaxy to maintain its gas supply longer. They could also affect the morphology, creating elongated structures aligned with the field lines. Testing these ideas requires better observations and more sophisticated modeling. One intriguing possibility is that magnetic fields affect how feedback operates. When a supernova explodes, the expanding shell of hot gas interacts with the ambient magnetic field. If the field is strong, it can confine the expansion, channeling the ejecta along field lines rather than allowing it to disperse in all directions. This could create bipolar outflows, jets of material escaping along the galaxy's rotation axis while gas in the disk remains relatively undisturbed. Such geometry could explain how JWST-7329 maintains its star formation despite supernovae. The feedback escapes preferentially along the poles, carrying away energy and momentum but leaving the disk gas intact. It's a speculative idea, but one that could reconcile the apparent contradiction between strong feedback and continuing star formation. Now let me tell you about something that doesn't get enough attention: the role of cosmic rays. These are high-energy particles, mostly protons, accelerated by supernovae and other energetic processes. They pervade galaxies, carrying energy and driving chemistry. In the Milky Way, cosmic rays contribute significantly to heating the interstellar medium and ionizing molecular clouds. In the early universe, cosmic rays might have been even more important. With star formation proceeding intensely, with supernovae exploding frequently, the cosmic ray flux would have been high. These particles could have ionized gas, altered chemical reaction rates, and provided pressure support against collapse. They're an additional feedback mechanism, complementing thermal and kinetic feedback from supernovae. For JWST-7329, we have no direct measurements of cosmic rays. We can't detect them at such distances, but we can look for their effects. Cosmic rays ionize hydrogen molecules, creating H2+ ions that react with other species, driving specific chemical pathways. The products of these reactions, molecules like OH and CH+, might be detectable in the spectrum if present in sufficient quantities. Searches for these molecular tracers are ongoing. If detected, they would provide indirect evidence of cosmic ray activity, constraining the intensity of the cosmic ray flux. Combined with models of cosmic ray transport and interaction, this could tell us how important cosmic rays were in regulating star formation in the early universe. There's also a connection to the broader topic of feedback processes. We've talked about supernovae, but they're not the only feedback mechanism. Stellar winds from massive stars, before they explode, also inject energy and momentum into the interstellar medium. Radiation pressure from young stars can push on gas and dust, creating outflows. Active galactic nuclei, if present, can drive powerful jets and winds. Each feedback mechanism operates on different scales and timescales. Stellar winds are continuous but relatively gentle. Supernovae are sporadic but violent. AGN feedback, when active, can be extremely powerful, potentially ejecting gas from the entire galaxy. The net effect depends on which mechanisms dominate, which varies with galaxy properties and evolutionary state. For JWST-7329, we think supernovae are the primary feedback source. There's no evidence for an active galactic nucleus, no broad emission lines or X-ray emission characteristic of accreting black holes. Stellar winds likely contribute but are probably secondary. The key question is how efficiently supernovae couple their energy to the gas. How much energy goes into heating and driving outflows versus being radiated away or carried off by cosmic rays. Simulations explore this parameter space, varying the efficiency of feedback and observing the results. High efficiency means most supernova energy goes into feedback, creating strong outflows and suppressing star formation. Low efficiency means energy is lost to radiation, allowing star formation to continue. By comparing simulated galaxies to observations of JWST-7329, we can constrain the feedback efficiency, learning how this process operated in the early universe. Let's talk about something personal: I remember when I first saw the spectrum of JWST-7329. Not the processed, publication-ready version, but the raw data fresh from the telescope. It was just squiggles on a screen, flux versus wavelength, noisy and requiring calibration. But even in that raw state, you could see the emission lines popping out of the background. Bright spikes at specific wavelengths, exactly where hydrogen and oxygen should be if redshifted by a factor of 13. There's something visceral about that moment. You're looking at photons that traveled across most of the universe's history to reach you. Photons emitted by stars that died billions of years ago, stars that formed when the universe was in its infancy. And those photons are hitting a detector, generating electrons, creating a signal that you're now analyzing. It's as close to touching the past as you can get in physics. That spectrum represents information. Encoded in the wavelengths and intensities of those spectral lines is a story about how stars formed, how gas was ionized, how elements were created and dispersed. Our job as astronomers is to decode that story, to extract meaning from the photons. It's detective work, forensic analysis of ancient light. And it's humbling, because those stars don't know we're looking at them. They don't care. They lived and died according to the laws of physics, indifferent to whether anyone would ever observe them. We're the ones who care, who find meaning in their light, who construct narratives about their existence. The universe provides the data, we provide the interpretation. This separation between data and interpretation is crucial. The spectrum of JWST-7329 is objective, a physical record of photons detected. But what we conclude from that spectrum, the models we build, the theories we construct, those are interpretations. They're our attempt to make sense of the data, but they're not the data itself. They could be wrong, probably are wrong in some details. And that's okay because science is self-correcting. New observations will test our interpretations, refining them, improving them, occasionally overturning them entirely. For JWST-7329, we're still in the early interpretation phase. The data is recent, the analysis ongoing. Different teams are reaching different conclusions, emphasizing different aspects, constructing different models. Over time, these interpretations will converge as more data arrives, as better models are developed, as the community debates and critiques and builds consensus. That's the process. Messy, human, imperfect, but ultimately effective at approaching truth. Now let me share something about the economics of this research. Building and operating telescopes like Webb costs billions of dollars. Analyzing the data requires supercomputers, expensive software, trained scientists with years of education. All of this requires funding, which comes ultimately from taxpayers through government agencies. Is it worth it? That's a fair question. With finite resources, we must make choices. Money spent on astronomy could be spent on healthcare, education, infrastructure, countless other priorities. Why choose to study distant galaxies? The easy answer is that fundamental research often has unexpected applications. Technology developed for astronomy finds uses elsewhere. CCD cameras, invented for telescopes, now power smartphones. GPS satellites use relativistic corrections discovered by studying gravity. Medical imaging techniques derive from astronomical image processing. The return on investment, measured in technological spin-offs, is substantial. But I think there's a deeper answer. We don't fund astronomy purely for practical benefits. We fund it because understanding the universe is inherently valuable. Because knowledge for its own sake enriches humanity. Because a society that values curiosity, that supports the pursuit of understanding, even when immediate applications aren't obvious, is a healthier, more vibrant society. JWST-7329 won't cure diseases. It won't generate economic growth. It won't solve climate change, but it will expand human knowledge. It will answer questions about our cosmic origins. It will inspire young people to pursue science. And it will remind us that we're part of something vast and ancient and magnificent. That's worth funding. That's worth supporting. Not at the expense of other priorities, but alongside them. A society can walk and chew gum simultaneously. We can address immediate needs while also pursuing long-term goals like understanding the universe. The scientists studying JWST-7329 are acutely aware of this responsibility. They're using public resources, taxpayer money, to pursue their research. That comes with an obligation to communicate findings, to justify the investment, to demonstrate the value of their work. Not in crass economic terms, but in terms of advancing knowledge and enriching human understanding. This is why outreach matters. Why scientists give public lectures, write popular articles, engage on social media. They're not just talking to each other. They're talking to the public that funds their research. They're explaining what they do and why it matters. They're fulfilling a social contract between science and society. For JWST-7329, the outreach has been extensive. Press releases, interviews, social media posts, all explaining the discovery and its significance. Not everyone will understand the technical details, but that's okay. What matters is conveying the excitement, the sense of discovery, the idea that we're learning something new about the universe. And the response has been positive. People are interested. They want to know about distant galaxies, about cosmic history, about our place in the universe. This hunger for knowledge is universal, transcending education levels and cultural backgrounds. It's part of being human, this curiosity about existence. Let me tell you about the international dimension of this work. The discovery of JWST-7329 involved scientists from dozens of countries. The telescope itself was built through collaboration between NASA, ESA, and CSA space agencies from the United States, Europe, and Canada. The scientists analyzing the data come from universities and institutes worldwide. This international character is typical of modern astronomy. The problems are too complex, the instruments too expensive, the datasets too large for any single nation to tackle alone. We need to pool expertise, share resources, collaborate across borders. And generally, this works remarkably well. There are challenges, of course. Time zone differences complicate meetings. Language barriers require accommodation. Different institutional cultures and funding systems create friction. But the shared commitment to science, the common goal of understanding the universe, bridges these differences. Scientists find ways to work together, setting aside national rivalries in pursuit of knowledge. JWST-7329 exemplifies this cooperation. The discovery team includes members from multiple countries, communicating via video calls and email, sharing data through cloud storage, collaborating on papers that list authors from institutions around the globe. It's a model of how international collaboration should work, and a reminder that science transcends politics. But it's also fragile. International cooperation requires trust, requires continued commitment from all parties, requires funding that can be threatened by budget cuts or political changes. The scientific community works to maintain these collaborations, to demonstrate their value, to argue for continued support. It's not guaranteed. It requires constant effort. The future of astronomy depends on maintaining this international framework. The next generation of telescopes, even more ambitious than Webb, will require even greater cooperation. No single country can afford them alone. We need to work together to pool resources, to maintain the infrastructure that enables discovery. JWST-7329 is a product of this cooperation. It exists as a scientific discovery because people from different countries chose to work together toward a common goal. That's worth celebrating and worth defending. Let's discuss the educational implications. Discoveries like JWST-7329 change how we teach astronomy. Textbooks need updating. Curricula need revision. Students need to learn about the latest findings, not just historical facts. And educators need resources to make this material accessible and engaging. For JWST-7329, educational materials are already being developed. Lesson plans explaining galaxy formation, activities where students analyze simulated spectra, visualizations showing the galaxy's place in cosmic history. These materials make cutting-edge research accessible to students at various levels, from elementary school through university. This is important because it demonstrates that science is ongoing, that discoveries happen now, not just in the past. Students often perceive science as a collection of established facts, dead knowledge to be memorized. But science is alive, dynamic, constantly evolving. Introducing current research into education combats this misconception, showing students that science is an active process of discovery. It also inspires. Learning about JWST-7329, about how it challenges our understanding, excites students. It shows them that there are still mysteries to solve, questions to answer, discoveries to be made. Some of those students will become the next generation of astronomers, continuing the work of unraveling cosmic history. The discovery feeds back into education, which feeds back into future discoveries. It's a virtuous cycle. Educators face challenges in incorporating new research. Textbooks lag behind the cutting edge, sometimes by years. Teachers may not have training in the latest findings. Resources may not exist in accessible forms. But dedicated educators find ways, supplementing textbooks with recent articles, incorporating news about discoveries like JWST-7329 into their teaching. The astronomy community tries to help. Many universities and research institutes maintain education and public outreach programs, creating materials that teachers can use. Professional societies hold workshops for educators, training them on current research and providing resources. Individual scientists visit schools, give talks, answer questions. All of this supports the integration of discoveries like JWST-7329 into education. And it's bidirectional. Students ask questions that scientists haven't considered. Fresh perspectives from young minds can spark new ideas. The public engagement process enriches science itself, not just the audience. It's not a one-way transfer of knowledge from expert to novice, but a conversation where both parties benefit. Now let's consider what JWST-7329 tells us about the Milky Way's own history. Our galaxy didn't spring into existence fully formed. It assembled over billions of years, growing through mergers and accretion. In its youth, the Milky Way probably looked very different than it does today. Smaller, more chaotic, actively forming stars at high rates. Could the Milky Way have gone through a phase similar to JWST-7329? Could it have been, at some early epoch, a collection of small star-forming clumps gradually assembling into a larger structure? The hierarchical formation model suggests yes. Our galaxy's building blocks might have been objects not unlike JWST-7329, dozens or hundreds of small galaxies merging over time. Evidence for this history exists in the Milky Way's stellar populations. Old stars in the halo show chemical signatures consistent with formation in smaller systems that were later accreted. Stellar streams, tidal debris from disrupted satellites, trace the paths of ancient mergers. The structure of our galaxy bears the imprint of its assembly history. By studying galaxies like JWST-7329, we're looking at possible ancestors of the Milky Way. Not direct ancestors, since this particular galaxy is in a different part of the universe and its future evolution will be different. But analogs, systems that show what the Milky Way's building blocks might have looked like. This connection makes the research personal. We're not just studying some abstract, distant object. We're studying our own history, tracing back the chain of events that led to our existence. The stars in JWST-7329 might be similar to the oldest stars in the Milky Way, formed in similar conditions through similar processes. Understanding one helps us understand the other. There's also a connection to the local group, the collection of galaxies including the Milky Way and Andromeda. This group contains numerous dwarf galaxies, small systems that orbit the larger spirals. Some of these dwarfs are still forming stars, while others are quiescent, having exhausted their gas. Could they be descended from objects like JWST-7329? Could they represent evolved versions of these early star-forming dwarfs? The answer is complicated. Some local group dwarfs probably formed relatively recently, coalescing from gas expelled during interactions between the Milky Way and Andromeda. Others might be ancient, forming in the early universe and surviving to the present. Distinguishing these populations requires careful analysis of their stellar content and chemical composition. What we can say is that JWST JWST-7329 provides context. It shows that small star-forming galaxies existed in the early universe, that they were capable of enriching their gas and building stellar populations. This supports the idea that at least some local group dwarfs are ancient survivors, relics from cosmic dawn. Let's talk about the connection to exoplanets and astrobiology. It might seem like a stretch, linking a distant galaxy to the search for life. But there's a real connection through the chemical enrichment process. Life, as we know it, requires heavy elements. Carbon for organic molecules, nitrogen for amino acids, oxygen for water and respiration, phosphorus for DNA. These elements don't exist primordially. They're created in stars and dispersed by supernovae. Without multiple generations of star formation, without chemical enrichment, planets would be lifeless balls of hydrogen and helium. JWST-7329 is participating in this enrichment process. Its stars are fusing hydrogen and helium into heavier elements. When those stars die, they'll disperse those elements into space. Eventually, perhaps after billions of years of additional enrichment, some gas cloud enriched by these processes will collapse to form new stars and planets. And some of those planets might be habitable with the right combination of elements to support life. So in a very real sense, galaxies like JWST-7329 are making life possible. They're creating the elements that biology requires. They're setting the stage for the emergence of complexity, of chemistry, of life. The chain of causation is long and indirect, but it's real. This puts our own existence in context. The carbon in our bodies, the iron in our blood, the calcium in our bones, all were created in stars. Some of those stars might have existed in small, early galaxies not unlike JWST-7329. We're connected to the cosmic dawn, descendants of processes that began when the universe was young. There's something profound about this realization. We're not separate from the universe. We're part of it, made of it, products of its evolution. The atoms in your body are billions of years old, forged in stellar furnaces, dispersed by supernovae, incorporated into our solar system, assembled into planets, and eventually into living organisms. You're a collection of stardust, temporarily arranged in a form capable of contemplating the cosmos. JWST-7329 reminds us of this connection. It's part of the same grand process that eventually led to us. By studying it, we're studying our origins, tracing back the chain of cosmic evolution from the Big Bang to the present, from the first stars to conscious beings pondering their existence. Now let me address criticisms and controversies, because they exist. Not everyone agrees about the interpretation of JWST-7329. Some astronomers argue that the galaxy isn't as anomalous as claimed, that it fits within the uncertainties of existing models. Others suggest that the measurements might be wrong, that the size or mass estimates are uncertain enough that the galaxy might actually be consistent with predictions. These are legitimate criticisms worth taking seriously. Science progresses through skepticism, through questioning claims, through demanding rigorous evidence. The astronomers who discovered JWST-7329 welcome this scrutiny. They've presented their evidence, explained their methodology, acknowledged uncertainties. Now the community evaluates, critiques, and ultimately judges whether the claims hold up. Some specific criticisms focus on the size measurement. Determining a galaxy's size from Webb images requires modeling its light profile, fitting models to the observed brightness distribution. Different models give slightly different sizes. If you use a more generous definition of size, including faint outer regions, JWST-7329 appears larger, less anomalous. The discoverers argue that their size estimate is standard and conservative, but the debate continues. Other criticisms target the stellar mass estimate. This is derived from the integrated light and spectral properties using stellar population synthesis models. But these models have uncertainties, especially for unusual stellar populations or different initial mass functions. If the model assumptions are wrong, the derived mass could be off, changing the interpretation. These technical debates might seem esoteric, but they're crucial. The significance of JWST-7329 depends on getting the measurements right. If the size is larger or the mass is higher than initially estimated, the galaxy becomes less exceptional, more consistent with existing models. The discovery would still be interesting, but not as revolutionary. My take is that even with conservative estimates, JWST-7329 remains noteworthy. It's clearly a small, efficiently star-forming galaxy at very high redshift. The exact degree of its anomalousness is debatable, but its existence at all is significant. It's pushing against the boundaries of what models predict, even if not completely outside those boundaries. That's still valuable scientifically. Moreover, JWST-7329 isn't alone. The existence of a population of similar objects, even if individually less extreme, is important. It suggests that our understanding of dwarf galaxy formation in the early universe needs refinement. Whether that refinement is a minor adjustment or a major overhaul is the subject of ongoing research. The controversy is healthy. It's driving more observations, better analysis, improved models. Whether JWST-7329 ends up being a genuine paradigm shifter or just an interesting outlier, the science benefits from the debate. We'll understand early galaxy formation better because of the scrutiny this object has received. Let's discuss predictions. What do we expect Webb to find as it continues surveying the early universe? Based on what we've learned from JWST-7329 and its siblings, we can make educated guesses. First, we'll probably find more small star-forming galaxies at high redshift. The initial discoveries suggest they're more common than previous models predicted. As Webb accumulates more observing time, surveying larger areas and going deeper, the census will improve. We'll map out the luminosity function, understanding the relative abundances of galaxies at different masses and luminosities. Second, we'll likely discover even more extreme examples. JWST-7329 is remarkable, but probably not the most extreme object out there. Statistical theory suggests that for every moderately unusual object you find, there should be rarer, more extreme examples lurking below detection limits or in unexplored parameter space. Webb might find even smaller, even more efficiently star-forming galaxies, pushing our models to greater extremes. Third, we'll probably find objects that don't fit into current categories. Galaxy classification schemes evolved to describe nearby galaxies: spirals, ellipticals, irregulars. But the early universe might have hosted galaxy types that no longer exist, evolutionary stages without modern analogs. Webb gives us our first good look at this epoch, and we should expect surprises. Fourth, we'll likely find more connections between early galaxies and other phenomena. Links between galaxy properties and reionization. Connections between star formation histories and black hole growth. Relationships between environment and evolution. Each discovery provides context, showing how different aspects of cosmic history interweave. Fifth, we might find evidence for physics beyond our current understanding. This is speculative but exciting. If galaxy formation in the early universe proceeds fundamentally differently than we think, it might point toward new physics. Modified gravity theories, alternative dark matter models, novel feedback processes, all could leave signatures in the galaxy population. Webb's observations will constrain these possibilities. These predictions aren't certain. The universe has surprised us before and will surprise us again. But they're reasonable extrapolations based on what we've learned so far. And they're testable. Over the next several years, Webb's observations will confirm or refute these predictions, refining our understanding. The timeline matters. Webb is designed for at least a 10-year mission, possibly longer. That's a decade of observations, of discoveries, of accumulated data. The full impact of the telescope won't be apparent for years. JWST-7329 is just the beginning, an appetizer before the main course. The best discoveries might still be ahead of us. Now let me tell you what keeps me excited about astronomy. It's not just the discoveries themselves, though those are thrilling. It's the process, the journey from ignorance to understanding. It's the puzzle solving, the detective work, the gradual assembly of pieces into a coherent picture. JWST-7329 embodies this process. We found something unexpected. We're working to understand it. We're developing hypotheses, making predictions, testing ideas. Some will prove correct, others wrong. But through this process, our understanding will deepen. We'll learn not just about this particular galaxy, but about galaxy formation generally, about the early universe, about the processes that shaped cosmic history. And that knowledge is permanent. Once we understand something, once we've figured out how it works, that understanding persists. It gets incorporated into textbooks, taught to students, built upon by future researchers. Scientific knowledge is cumulative, each generation adding to the foundation laid by previous generations. We're contributing to that edifice. Every observation of JWST-7329, every paper analyzing its properties, every model attempting to explain its existence, adds a brick to the structure of human knowledge. Individually, these contributions might seem small, but collectively, over time, they build something magnificent. A comprehensive understanding of how the universe works. That's the larger project we're part of. Not just studying one galaxy, but understanding the cosmos. Not just answering one question, but illuminating the fundamental nature of reality. It's an ambitious goal, perhaps unachievable in any final sense, but worth pursuing nonetheless. Because the pursuit itself is valuable. The act of seeking understanding, of asking questions and working to answer them, enriches us as individuals and as a species. It exercises our cognitive abilities, develops our rational faculties, connects us to something larger than ourselves. It's deeply human, this quest for knowledge, and engaging in it is one of the most meaningful things we can do. JWST-7329 offers that opportunity. A chance to engage with fundamental questions about existence. A chance to contribute to human understanding. A chance to be part of the grand scientific project that spans generations and cultures. That's why astronomers devote their careers to studying distant galaxies. Not for fame or fortune, though those occasionally come, but for the intrinsic satisfaction of understanding, of solving puzzles, of revealing nature's secrets. Let me share one final technical point before we wrap up. There's discussion about using JWST-7329 as a test case for next-generation simulations. The object is well observed, with high-quality data across multiple wavelengths. It has interesting, challenging properties that strain current models. That makes it an ideal benchmark for validating new simulation techniques. Several groups are developing targeted simulations, zoom-in runs that follow the formation of a small galaxy in detail. These simulations start from cosmological initial conditions but focus computational resources on a specific region, achieving resolution high enough to resolve individual star-forming clouds. They include sophisticated physics, magnetic fields, radiation transport, cosmic ray propagation, detailed chemistry. The goal is to reproduce JWST-7329's observed properties. Its mass, size, star formation rate, chemical composition, stellar population. If a simulation can match all these observables, it suggests the physics is correct, that we understand the relevant processes. If not, it points toward missing or incorrect physics. These simulations are computationally expensive, requiring months of runtime on supercomputers. But they're worth the investment because they provide insights impossible to obtain otherwise. We can track individual gas clouds as they collapse, follow stars from birth to death, see how feedback shapes the galaxy's evolution. We can run counterfactuals, turning off specific physics to see its importance. The results are emerging now, with papers being published and presented at conferences. Some simulations successfully reproduce JWST-7329's properties, suggesting our understanding is roughly correct. Others struggle, failing to match certain observables, pointing toward gaps in our knowledge. This back and forth between simulation and observation is driving rapid progress. In a few years, we'll have a much clearer picture. Simulations will have converged on the relevant physics. Observations will have expanded the sample size, providing better statistics. Theory will have caught up with observation, providing explanations for the early galaxy population. JWST-7329 will be understood, its mysteries resolved, its place in cosmic history clarified. But new mysteries will have emerged. That's the nature of science. Answering questions raises new questions. Solving puzzles reveals deeper puzzles. It's an endless process, and that's what makes it exciting. There's always more to learn, always new phenomena to explore, always another layer of understanding to uncover. So as we approach the conclusion of this exploration, let me tie together the threads we've followed. JWST-7329 is a small galaxy in the early universe, existing when it shouldn't, challenging our models of how galaxies form. Its discovery by the James Webb Space Telescope represents cutting-edge observational astronomy, pushing technology to its limits to reveal faint objects at cosmic dawn. The galaxy's properties, its size and mass and star formation rate, don't fit comfortably within existing theoretical frameworks. It's too small, too efficient, too successful at forming stars given what we know about feedback and gas dynamics. This has sparked intensive research, with observers gathering more data and theorists developing new models to explain the anomaly. Several explanations are under consideration. Perhaps the galaxy sits in an unusually concentrated dark matter halo, providing extra gravitational binding. Perhaps star formation proceeds in bursts rather than continuously, allowing the galaxy to evade the worst effects of feedback. Perhaps feedback operates differently in the early universe than in local galaxies. Perhaps our simulations miss crucial physics or use incorrect parameters. We don't yet know which explanation is correct. Multiple hypotheses are being tested, multiple approaches being tried. This is normal in science, especially when dealing with new phenomena that challenge established understanding. The process takes time, requires patience, demands rigor, but it works, gradually converging on truth through repeated testing and refinement. The broader significance of JWST-7329 extends beyond this one object. It's part of a population of small star-forming galaxies in the early universe, a population that appears more abundant than previous models predicted. These galaxies might have played a crucial role in cosmic reionization, producing the ultraviolet radiation that ionized the intergalactic medium. They represent the building blocks from which larger galaxies, perhaps including our own Milky Way, eventually assembled. Understanding these galaxies requires multi-pronged approach. Observations with Webb and other telescopes provide the data. Simulations model the physics, testing hypotheses and making predictions. Theory provides the conceptual framework, explaining phenomena in terms of fundamental principles. All three components, observation, simulation, and theory, work together, informing and constraining each other. The research is ongoing, far from complete. More observations are planned. New simulations are running. Papers are being written, conferences are being held, debates are being conducted. Over the coming years, our understanding will crystallize. Questions that seem baffling now will become clear. Mysteries will be solved or at least better understood. But science is never finished. Solving one mystery reveals others. Understanding JWST-7329 will lead to new questions about galaxy formation, about the early universe, about the processes that shape cosmic evolution. And those questions will drive the next generation of research, continuing the cycle of discovery that has characterized astronomy for centuries. This is the scientific endeavor at its finest, an iterative process of observation, hypothesis, testing, and refinement, a collaborative effort involving researchers around the world, a human activity driven by curiosity, by the desire to understand, by the conviction that knowledge is worth pursuing for its own sake. JWST-7329 exemplifies all of this, a single galaxy that has become a focal point for exploring fundamental questions about the universe. And it reminds us of something important. The universe is under no obligation to conform to our expectations. We build models based on observations, extrapolate to new regimes, make predictions. Sometimes those predictions are confirmed. Sometimes they're not. When they're not, when the universe surprises us, that's when we learn the most. That's when science advances, when paradigms shift, when understanding deepens. JWST-7329 surprised us. It exists when it shouldn't, at least according to our models. That surprise is a gift, an opportunity to learn, a signpost pointing toward incomplete understanding. Rather than being frustrated by anomalies, we should celebrate them. They're how we make progress, how we move beyond current knowledge toward deeper truth. The story of JWST-7329 is still being written. We're in the middle chapters with the ending not yet visible. But we can be confident that the ending, when it comes, will involve deeper understanding of galaxy formation, of the early universe, of the cosmic processes that eventually led to our existence. We'll look back on this discovery as a turning point, a moment when our understanding shifted, when we realized that the early universe was richer and more complex than we had imagined. And perhaps, years from now, some student will read about JWST-7329 in a textbook. They'll learn how it was discovered, what it taught us, how it changed our understanding. They'll see it as historical fact, established knowledge, part of the foundation on which they build their own research. And they won't fully appreciate the uncertainty we felt, the debates we had, the excitement of discovery. To them, it will just be another galaxy, interesting but not revolutionary, because the revolution will be complete, the knowledge integrated, the anomaly explained. But we're living through that revolution now. We're witnessing the discovery, participating in the debate, experiencing the uncertainty. We don't know how it will end, what conclusions we'll reach, what new understanding will emerge. But that uncertainty is part of the thrill. That's what makes this moment special. This time in astronomical history, when Webb is revealing the early universe and challenging our preconceptions. So here's to JWST-7329, a tiny galaxy that shouldn't exist but does, a puzzle that challenged our understanding and forced us to think harder, to question assumptions, to develop new models. A reminder that the universe is full of surprises, that our knowledge is incomplete, that there's always more to learn. Here's to the astronomers studying it, dedicating their careers to understanding this enigmatic object. Here's to the engineers and technicians who built Webb, making observations like this possible. Here's to the funding agencies and governments that supported the mission, investing in knowledge for its own sake. Here's to humanity's curiosity, that insatiable desire to understand, to explore, to know. And here's to the future, to the discoveries yet to come, the mysteries yet to be revealed, the understanding yet to be achieved. Webb will continue observing, finding more galaxies, more surprises, more evidence that the universe is stranger and more wonderful than we imagine. Each discovery will add to our knowledge, bringing us closer to comprehensive understanding of cosmic history. We're fortunate to live in this era, an era when technology allows us to observe the distant universe, when our theories are sophisticated enough to make testable predictions, when international collaboration enables large-scale projects. Previous generations could only wonder about the early universe. Future generations might take this knowledge for granted. But we're in the sweet spot, witnessing revelations in real time, participating in the discovery process. JWST-7329 is part of our generation's contribution to astronomical knowledge. Along with discoveries of exoplanets, gravitational waves, dark energy, and countless other phenomena, it represents what we learned, what we added to the edifice of human understanding. Future astronomers will build on this foundation, just as we built on the foundation laid by previous generations. That's how science progresses, through accumulation, through collaboration across time as well as space. So as we conclude this exploration of JWST-7329, let's remember what it represents. It's not just a galaxy, it's a question mark in the sky, a challenge to our understanding, an invitation to think deeper and reach further. It's evidence that the cosmos still has secrets, that reality exceeds our models, that there's always another layer to uncover. It's a reminder of why we do science, why we explore, why we quest for understanding despite the difficulty and uncertainty. The tiny galaxy that shouldn't exist does exist, and its existence makes the universe more interesting, more complex, more worthy of study. It reminds us that we're just beginning to understand cosmic history, that our models are provisional, that nature has depths we haven't plumbed. And that's exactly how it should be. A universe fully understood would be less interesting than a universe full of mysteries. JWST-7329 ensures that we have mysteries to solve, questions to answer, discoveries to make. That's the final lesson. Not that we've figured it all out, but that there's still so much to figure out. Not that our models are perfect, but that they're improvable. Not that we understand the universe, but that we're making progress toward understanding it. JWST-7329 is a marker on that journey, a signpost indicating how far we've come and how far we have yet to go. The journey continues, the exploration proceeds, and the universe, in all its strangeness and beauty, awaits our continued investigation. In the end, JWST-7329 teaches us humility and wonder in equal measure. Humility because it shows that our understanding is incomplete, our models imperfect, our knowledge provisional. Wonder because it reveals that the universe is more magnificent than we imagined, full of phenomena that surprise and delight us, rich with complexity that rewards careful study. These twin lessons, humility and wonder, are essential for science. They keep us honest and keep us curious. They remind us why we do this work, why we spend careers studying distant objects that have no direct impact on daily life. Because understanding matters, because knowledge is valuable, because revealing nature's secrets is one of the noblest pursuits humans can undertake. JWST-7329, a tiny smudge of light from the cosmic dawn, embodies this pursuit. It's a testament to human curiosity, human ingenuity, human persistence. It represents our species at its best, looking outward, asking questions, seeking answers, refusing to accept ignorance when understanding is possible. And so we continue. We observe, we analyze, we theorize, we debate. We build better telescopes, develop better models, gather better data. We train the next generation of astronomers, passing on our knowledge and our curiosity. We communicate our findings to the public, sharing the wonder of discovery with everyone. This is our contribution to the human story. Not conquering or exploiting, but understanding. Not dominating nature, but appreciating it. Not imposing our will on the universe, but learning its ways. JWST-7329 is a chapter in this story, a chapter that demonstrates science at its best. Humble before nature, persistent in investigation, collaborative in execution, and excited by mystery. The universe gave us JWST-7329 as a gift. A puzzle wrapped in starlight, delivered across billions of light years and billions of years. Our job now is to unwrap that gift, to solve that puzzle, to understand what this galaxy tells us about cosmic history. We're making progress. We're getting closer. And someday, perhaps soon, we'll look back on this moment and smile at what we learned, grateful for the opportunity to expand human knowledge, proud to have played a part in the grand endeavor of understanding the cosmos. Until then, we keep working, keep observing, keep thinking, because that's what we do. That's who we are. And that tiny galaxy, existing against all odds, wouldn't have it any other way.